Due to technical difficulties, we now return to lecture previously in progress. Yeah, just like Dragon Ball Z. So, what is the advantage of this particular setup? What if I ask the probability of rolling the 2 die so that the sum is at 4? Well, that could happen with a 3 and a 1, a 2 and a 2, or a 3 and a 1. So I notice that all of them are on the same diagonal, all 3 of those outcomes. And I notice that it's easy to count how many possible outcomes we have, because I have a 6 by 6 square, so there are 36 outcomes. Do you have to draw one of these grid sample spaces? No. It's just one convenient way to maybe represent a sample space. The next one is called a tree diagram. Again, another way to represent a sample space. This one is probably much more, one that'd be much more likely to be used. And in fact, in my experience looking at the IB exams of the past, this is a favorite of theirs, is picking questions where it's definitively to your advantage to do something like this. So what a tree diagram looks like is, suppose we have the following example. Let's not see that. So let's say that we have a bag of 15 balls, and inside that bag we have 8 green balls and 7 red balls, and we're going to choose 2 balls from that bag with replacement. So that means after I pick one ball out of there, I drop it back in the bag, we mix it up again, and I draw out a second one. So I'm going to use like a tree diagram to kind of represent this. So I could either draw a green ball or a red ball with my first choice, correct? Now, if I draw a red ball, on my second draw I could also draw a red ball, or I could also draw a green ball. If I've drawn the green ball, on my second choice I could draw a red ball, or I could draw a green ball. Now, typically, we now would include the probabilities of each of these draws. We typically write the probabilities on the line. So I know there's 7 red balls in the bag and 15 total. So the probability of picking a red ball would be 7 out of 15. Similarly, there are 8 green balls and 15 total, so the probability of drawing a green would be 8 out of 15. For our second choice, since we've put the ball back in the bag, the probability of drawing red is still 7 out of 15, and green is still 8 out of 15. Yes, Max? Sure. So that's an example of a tree diagram. Let's now look at a table of outcomes. So let's say that we have a table of outcomes might look like, similar to what you guys had to do in your quiz that you just took for the first question. You could be given something like this. What this is really useful for are situations where you can have combined events. So suppose I wanted to choose, or wanted to find the probability of choosing a girl or a track athlete. You have to be careful because there are girls who are also track athletes. So these kind of tables are closely related to the Venn diagrams that we've been making before and are often useful in these situations where you can have a combined event, where you can have, unlike flipping a coin, where you can't have heads and tails happening at the same time, a situation like this, you could have a girl that also does, one of these two sports. So you could do a Venn diagram. These are often useful. So say that you had something like a set of students that took chemistry and biology classes, and we wanted to say the probability that you took chemistry or biology. Again, you have to be a little bit careful because there are a number of students that do both of those things. So a Venn diagram is a useful way to kind of sort that out to make sure you're not double counting anything. And then a pie chart is nice. So imagine you're playing Wheel of Fortune. If you've watched Wheel of Fortune recently, you'll notice that there are spots where the sectors of the wheel aren't the same size. Usually what they do is they'll do what they do now is they have like one little tiny sliver with like the $1 million spot, but then you have bankrupts on the side of it. So they change the probability of hitting that $1 million by making it smaller than all the rest of them, and then surrounding it by bad things. But this is, to do this, you're basically doing geometric probability, so that the size of that sector is directly proportional to the probability of landing in that sector. So let's just do a couple of quick examples here. Let's say that we're electing a board for a company. There are candidates A, B, C, D, E, and 2 spaces on the board. Yes. What are the possible boards? How many of these things should we have? Who remembers this from their Algebra 3-4 class from many moons ago? Yeah, this is a combinations question. If you remember, this is going to be 5 choose 2. Right? You have 5 choices, and you need to pick 2 things from that set. If you do that on your calculator, 5 choose 2 is 20, I think. So let's see. You could have A and B. You could have A and C. You could have A and D. You could have A and E. Everybody agree with that? Now let's do the B's. We've already done A and B. So we have B and C, B and D, B and E. Now let's do the C's. We've already done AC, already done BC. We can do CD or CE. Now let's do the D's. We've done AD, BD, and CD. That leaves us with just DE. And there's no more E's to do. I was wrong. That's definitely not what that equals. I forgot about that. Oops, I did the wrong formula in my head. What is it really going to be here? 10. I apologize. So this is your sample space. What do you guys think? Yeah. So if we asked, what's the probability that the board contains candidate A? We have 4 A's out of 10 possibilities, so 0.4 or 40%. Everybody pretty happy with that? Okay. That's section 2. Section 3 is calculating probability. I don't know why we need a new section for this, because we've been doing it in all the sections already, but that's usually how probability works. So the definition for probability of A is just the number of outcomes of A divided by the total number of outcomes. Or if you prefer the more set notational definition, you can say it's the cardinality of A divided by the cardinality of the universal set, or the sample space, really is what you're talking about. So let's look at an example here of doing some of these. I think this whole section is just like getting comfortable doing these kinds of things. So we have the numbers 1 through 10 placed in a bag, written on a separate sheet of paper, folded up. You're blindfolded, reach into the bag, and we want to find the probability and pull out a single one of these numbers. So what's the probability that we get a prime? Well, that's going to be the number of primes divided by total number of numbers. How many primes do we have between 1 and 10? 2, 3, 5, and 7 are all prime. And how many numbers are there from 1 to 10? Shockingly, there's 10. So 4 or 40%. How about the probability that we draw a multiple of 5? 2 out of 10 is correct. How about the probability of picking 0? Correct. How about the probability that we pick a number from 1 to 10? That's 10 out of 10, or 100%. How about the probability of not a prime? You could do it the easy way, or you could do it the hard way. I'm going to choose to do it the easy way. I remember this is the same thing as 1 minus the probability of a prime. We already did that. So 6 out of 10. Could you have also done it by counting up all the non-primes? Sure. Which one was faster? Since we had already done the work, I like using the complement. That's a nice little trick. Let's say we have 2 dice are rolled, and we want the probability that the total, I should say, sum is 6. So if we go back, we already drew the sample space for this earlier. There it is. Where is the sample space of 6 at? Bless you. It's this spot right here, correct? Because 5 plus 1 is 6, 4 plus 2 is 6, 3 plus 3 is 6, 4 plus 2 is 6, etc., etc., etc. Everybody agree with that? So how many do we have there? I count 5 dots out of how many total? 36, so that's just 5 out of 36. What if we have the sum is at least 8? Well, let's go back to our picture here. I scrolled past it. I just got excited. So, let's see. We could have 6 and 2 is 8, 5 and 3, 4 and 4, 3 and 5, 6 and 2. But we could also have all of these spots, right? Because this is the 9 diagonal, the 10 diagonal, the 11 diagonal, the 12 diagonal. All of those are bigger than 8, correct? So how many total things do I got there? 5 plus 4 plus 3 plus 2 plus 1 is 15, I think. And I guess if you wanted to, you could reduce that, but I'm not too worried about it. Does everybody feel reasonably okay doing things like this? So continuing on into this section, we can talk about theoretical and experimental probability. So I'm just going to kind of do this with an example. Let's say we're flipping a coin. Let's actually not say that. Let's use we're having a baby. I know. So the probability of that baby being a boy is 1 out of 2. Now, that is the theoretical. No, that's not exactly it. Because if you actually look in biology, the distribution of the genders for humans is not exactly 50-50, right? It tends to be like a little over 51 to a little under 48, or a little under 49. There's actually a slightly higher probability of having, I think, boys than girls. But it's not exactly 50-50. There's a slightly higher probability of one gender than the other. It's males. And whether that has some biological reason or some nutritional reason or a cultural reason or whatever, when we actually go and count up the birth rates for human beings, we don't get exactly the theoretical. Everybody agree with that? What we should say, though, is that if I took a graph of where this x-axis is number of births and the y-axis is the probability of a boy, and this is the theoretical, that as the number of births kind of increases, that should be kind of approaching the theoretical. So notice that at times it could bounce above or below the theoretical, that it could improve or not. Like it could get worse for a little while, but it's going to come back down, or it could get better for a little while, but it might diverge a little bit away. But typically as the number of births increase, the closer you're going to kind of get to that theoretical, or you approach that theoretical. So if you could conceivably have an infinite number of births, we'd expect, if it's a fair experiment, to approach that theoretical. What kind of things could be going on to make it not a fair experiment? Like parents might be stopping pregnancies for a gender they don't desire or something like that, right? So that could be something that's like skewing this as an experiment. Okay with that idea? So let's do this kind of just for fun, for funsies. Let's say that we are tossing a coin. I have a coin right here. Zach, you be my tosser. Good hands.
I feel like you won. I do.
All right. So let's say we're going to do 2 times. The theoretical, I should have 1 tail, 1 head. Experimentally, Zach, flip that coin 2 times and tell us what we get.
All right. See, there's a tail.
Okay.
And then another tail.
Just to kind of illustrate this. So if we do this 4 times, we'd expect to have 2 tails and 2 heads, right? Toss that 4 times for, or 2 more times for us anyways.
A head. A tail.
So we started off at 100% tails. Now we're down to 75% tails. Let's now do this 8 times, so we'll do it 4 more times. Again, we'd expect 4 tails, 4 heads. So Zach, flip that for us 4 more times.
All right. See, there's a head. A tail. A head. A tail.
So now we have 5 tails and 3 heads, so that's like 62.5% tails. So you see that as this is going on, it seems like we're getting closer and closer to the theoretical 50% tails, 50% heads that we'd expect, right? I would. You may. Does everybody feel okay about the difference between the theoretical and experimental probabilities? Okay. The next one is section 4. This is about mutually exclusive events. So what do we mean by mutually exclusive events? Example, if we're talking about tossing a coin, heads and tails are mutually exclusive because you can't toss a coin and get both heads and tails as an outcome. Everybody okay with that? If you are running a race, you couldn't get both first place and second place. The finish of a race could be a mutually exclusive event. As opposed to me randomly selecting students from this classroom. I could randomly select a female student and a blonde student, and that's going to, female students or blonde students, and there's people in that, right? There are people that are 2 things at once, right? Like Lauren or Emma, right? Everybody okay with the idea for mutually exclusive? So the technical definition says if P of A plus P of B equals P of A union B, and the probability of the intersection is 0 or empty. That shouldn't say empty there, that should say 0, or you could say that the set is empty. Then A and B are mutually exclusive. And I don't know why it says this as an if-then. This is really if and only if. This could read both directions. So this is a very simple idea, but very powerful. Let's do an example to kind of illustrate this. So let's say we have a bag of marbles. We have 9 reds. We have 12 greens. And we have 11 yellows. And I want to say the probability of drawing a green. What would that be? $12 out of 32, right? The probability of drawing a yellow or a red. Are these mutually exclusive events? Can I draw a marble that's both yellow and red? No. So I could do this as the probability of yellows plus the probability of reds. So 11 out of 32 plus 9 out of 32 to give me 20 out of 32. We feel okay there? Okay. Let's do one more maybe. So let's say we have 28 IB students that are working in the library. We have 5 of them studying HL Math and 14 studying SL Math. And if we randomly select one of them, what's the probability that we select an HL student? That's 5 out of 28. The probability we select an HL or SL student, that probability is, are these mutually exclusive? Can you take 2 IB classes in the same subject area like that? You can't take IB Bio and, or HL Bio and then IB SL Bio at the same time. You can't do that. Yep. So those are mutually exclusive. Could you imagine having to do 2 bio internal assessments that have to be different? What if I wanted the probability of not HL or not SL? We'll just use the complement property to do that. Are we out of time? 10 minutes. Okay. Well, let's keep going then. Well, it's either we do it now or we do it some other time. So section 5 is about combined events. What do we mean by combined events? We mean the situation where this is true. So when we have, basically it means when we have something in the intersection. So let's look at an example here. Let's say this is the set of people who have gas stoves and electric stoves, and there's some weirdo that have 5 people that have both an electric stove and a gas stove. I don't know why. And 7 super weirdos that don't have any gas or electric stove at all. They must be living in like a log cabin mailing letter bombs to people. So if I wanted to find the probability of P union E, well, these are combined events because the intersection is non-empty, right? If I follow the definition, that's going to be P of G plus P of E minus P of G intersect E, correct? P of G is 23, and there's 42 total if you added them up. And then P of E is going to be 17 out of 42 total minus 5 out of 42. And that gives us 35 out of 42. Now, did you have to do it that way? Notice that this is also the same thing as P of G intersect E complement plus P of G intersect E plus P of G complement intersect E. What's the advantage here? These are all mutually exclusive. Why is that? Well, let's do some coloring. Whoa, I didn't mean to erase that part. So G intersect E complement is this part. G intersect E is that part. And G complement intersect E is that part. You notice there's no overlap between those two sets, which is probably the way you would have tried to do this in your head had you read this question. You would have just said 18 plus 5 plus 12 divided by the total, right? Which is perfectly fine. Not incorrect to do that. I just want to show you that you're not actually using the combined events formula that you're using. You're just creating mutually exclusive sets and then using the mutually exclusive formula. That's all you've done there, which is fine. There's nothing wrong with doing that. But there is a subtle little difference as to what you're doing. And I want to make sure that, we touch on that. Oh, boy. So we're going to stop here with the next thing we need to talk about is independent events. So that'll be the next thing up.